Hello, everybody, and welcome to our latest Hubble Hangout. My name is Tony Darnell, and I work at the Space Telescope Science Institute. And with me today we're going to have a great conversation about a new technique that involves using the Hubble Space Telescope to measure stellar distances. And with me today is Dr. Carol Christian. She is the Hubble Space Telescope Science Outreach astronomer. Hi, Carol.
There's my little wave.
Yeah, the royal we. Also with me is Scott Lewis, co-hosting. Hi, Scott. And
how's it going, Tony?
Good. And Dr. Ian O'Neill. He's the space editor for Discovery.com or DiscoveryNews.com. Hi, Ian. Thanks for coming.
Hi, Tony. Thanks for having me.
Yeah, thanks for being here. Also, I'm very pleased to have in our Hangouts for the second time now, Dr. Adam Rees. He's an astronomer at the Johns Hopkins University and Space Telescope Science Institute, and a Nobel laureate from 2011. Hi, Adam. Thank you for joining us.
Hey.
And Dr. Stefano.
Good to be here for the second time.
Yeah. You're also is Stefano Casertano from the Space Telescope Science Institute, an astronomer who has worked with Dr. Rees on this new technique. So let's go ahead and get started. But before we do, I want to mention that you can interact with us in a lot of different ways. You can leave comments and questions on our Q&A app on the Google event page. You can also tweet using the Hubble hashtag or Hubble Hangout hashtag. Whew, a lot of H's.
Oh, that's
Hubble Hangout hashtag. You can also leave comments on the YouTube watch page where this is being broadcast. So we hope you will leave us some comments and questions, and we'll get to them hopefully by the time before we have to close out the Hangout. So, Carol.
Yes.
How are you?
I'm good. How are you?
I'm good too. I want to talk about stellar distances, and I wonder if you could give us a background, just a little bit of background on how do we know how far away stuff is out there.
Yeah, exactly. So this will be a really short, because there are many methods, because astronomers are very clever, and the thing is that we can't go there. So on Earth, of course, we use a tape measure or a ruler, and we also use surveying. So you probably either have used survey tools, or you've seen people use surveys, like to measure a road, a building, something like that. And the way that works really is that you take a reading from one position, and then you move to another position, and you use geometry. You know the distance between your two measuring positions, and then you can figure out from geometry how far away something is. And so in astronomy, since the distance are far, we use actually the orbit of the Earth around the Sun. We know how big that distance is, so we take an observation on one side of the Sun, and then 6 months later on the other side. And usually, and there's the diagram showing that, and of course we take lots of measurements, not just two, and that gives us the distance to the star. But then we get to distances that are very hard to distinguish when we take the observation, even with Hubble, or traditionally with Hubble, and so the stars are too far away. So then we start using more indirect techniques, and we use things called standard candles, and we also use objects where we can model how bright we think they are, look at them and say, oh, they're a certain brightness, so the distance to them, understanding how light works, is then X or Y. So some of the objects that we're particularly interested in, more nearby objects, are called Cepheid variables. They change in a very particular way that we understand, and when we discover them and we measure how bright we see them, and we know how intrinsically bright they are, then we know the distance. And then there are other objects, and one of the most distant objects that we can use are supernova, and that's what Adam and his colleagues have been measuring. But it turns out that going back to the direct method, this parallax method is very powerful because it's a direct geometric measurement, and so there's no modeling or anything like that associated with it, and that's what Adam and his colleagues are going to talk about.
Okay, so so the geometric method you were talking about, that's called parallax, and up to now it's been, I think I read that it's the more reliable way, the most reliable way to measure how far away something is, because it's a direct measurement. We're actually...
Yes, it's a direct measurement, and we're not modeling anything. We're not saying, oh, the star or the galaxy or the cluster should be this bright or this temperature. We don't have to model anything. It's a direct measurement. It's just how we do surveying on the ground.
But it's not accurate, like you said. It's only good for a certain distance away, right? So, Adam...
Yeah, and then you can't take images that, I mean, traditionally telescopes couldn't take such precise measurements out to at a certain distance. Then you never see the star. It never changes place, so then you can't measure the distance.
Yeah, the way I always describe it to people is I say, look, you take your finger and you hold it out at arm's length.
Well, yes, that's parallax, because you have
that's right. That's what I'm saying with the parallax and
observation A, observation B.
Yeah, and you blink one eye and then the other, and you'll see if you look against the background walls, whatever object you're looking up against back there, it will appear to shift a little bit based on the distance, because the distance of each vantage point of each eyeball is a little bit different, and so the line of sight is slightly different. And so that's what the effect is we're talking about. And Adam, how good has this been traditionally as a technique for measuring things? Are you there?
Well, it's still pretty hard. Can you hear me?
Yep, I can hear you.
Yes.
Yep.
Are you hearing me, Tony?
Yep, okay. We can hear you.
You know, it's been hard simply because stars are really, really far away. Okay. Stars are just really far away, and so these angles, even when we use as a baseline the whole orbit of the Earth, those angles are incredibly small. Even for the very nearest stars, they're as small as 1 arcsecond, so 1/3600th of a degree.
Yeah, and how far away? When does this generally stop working? How far away are objects generally where you just can't see the shift anymore?
Right. So as technology has improved, we've been able to go further and further out, but that still is only out to a relatively small fraction of the Milky Way galaxy. So the Hipparcos satellite that the European Space Agency used in the 1980s could measure parallax to about 1 milli-arcsecond, which was good enough to get well-measured distances to stars that were, you know, something like under 100 parsecs, maybe 50 parsecs.
Okay, so can you what's that? So 50 parsecs. That's about what in roughly light years? I'm gonna have to know.
150 light year.
About 150.
Right.
Okay.
So with this new technique, we can measure well out to about 10,000 light years.
Oh, okay. So. Yeah, that's okay. Yeah, I want to get to that. So let's talk about this. I'm going to pull up this diagram that we have from the press release, and I would like you guys to talk about this a little bit. It says here that generally we're able to see things, you know, up to now, according to the way things have been done, about 750 light years away. But you guys have found a way to increase that by a factor of 10. What are you guys doing that makes it? I mean, that's quite a big jump. How a factor of 10?
Yeah.
I mean, wow. So what's going on here?
We just try really hard.
It's magical.
That makes most of the difference, it turns out.
Well, I guess
people have
a little bit of space elbow grease and you're good.
No, it's a very clever technique.
Well, let's hear about it. Let's hear about it. So, according to this diagram, now you can see things, or you can measure things reasonably well out to about 7,500 light years using this technique. And these are all, by the way, I should mention, stars. This obviously because of the distances involved. We're talking about things in our galaxy. So we're not talking about other galaxies or things like that. We're looking primarily in our own stellar neighborhood, more or less. So Stefano, what happened? The Hubble Space Telescope is almost 25 years old, and here you guys are figuring out new ways to make it even better. So what's the deal?
Well, what's happened is that we found a method. Adam and collaborators and myself have found a method to actually do 1,000 measurements in one image of the same object. So basically what happens is instead of taking a stellar field and staring at it for 10 minutes, which is the normal way of observing, what we do is we move the telescope while we are staring at it. And so that makes each star makes a long image where every piece of the image can be made as a separate measurement. And so over the course of 10 minutes, instead of making one measurement, we make 1,000.
Okay, you have something to illustrate this. Why don't you put that up real quick?
Yeah, let me try that. So what this is basically this is simulation really. It's too hard to do it for a real field, but it's a star field, and the square you see there is basically the imprint of the camera that we're using to look at it. And at the beginning, that's where the telescope is. Then the telescope starts moving, and I'm going to start the simulation here. And then we open the shutter, and these are the trails of each star, and each of them, gets observed many times over many pixels. In this camera.
So you're moving the telescope. You're moving the Hubble now.
Yeah, we're moving the telescope while we're taking the exposure, while the shutter of the camera is open. So basically, the stars all move, and that means that every time that you get a new image of the star, one pixel down, another pixel down, another pixel down, you make a new measurement of how far from each other all these stars are. And that basically turns out into over 1,000 measurements for each star, and that's in a single observation. So that's why we get a factor of almost 10, because we can, well, actually more than 10, because we make multiple observations every time.
Okay, I'm sorry, I'm having trouble getting this. So the actual measurement, the geometric measurement, is the shift in the background stars, right?
Right.
How do you get that from this star trail?
So we compare the stars to each other. Oh, sorry, go ahead.
Go ahead, Adam.
Well, I was just going to say, so the goal is every 6 months to measure the separation between our target star, the one we're trying to measure the distance to, and all the background stars. And we can only measure the position of a star so well. And so as Stefano described, by trailing the telescope, we're essentially getting 1,000 independent measurements of the separation between the target star and all the other stars. So we're leveraging the ability to make many measurements, and so we reduce the uncertainty by averaging.
So it's basically increasing the precision of your measurement, basically. And that's what's making it better?
So it increases the precision by about a factor of 10, and it's that precision which limits how far away you can measure stars, because when the stars become too far away, you can't tell that the target star has moved over 6 months. And so this allows us to detect smaller and smaller movements, which is to say further and further away stars.
So at one period in the orbit, then, in Earth's orbit, you take one of these fields and you do the thousands of measurements, and then 6 months later, the Earth is on the other side of its orbit, and farthest distance it can be from the previous measurement, and you do it again. And then you compare these two, which each of which have thousands of measurements in them. So statistically, you've got a lot more measurements than if you had just taken one image and looked at the star and measured those.
Yeah, precisely.
Okay.
That's right. And just to give you an idea how small these shifts are, we're looking.
Well, I'm sorry, Adam, but you're cutting out again. Can you? The last thing I heard was to give you an idea how small these shifts are. Are you there? Oh, I think. Did you?
Right. The shift. Yeah. Can you?
I'm sorry. Yeah, it's just not a good connection, Adam. I'm sorry.
Can you hear me?
Yeah, we got you now for a little bit. Yeah. Yeah, I'm sorry. It seems like that network is just not working for you. Yeah, the last thing we heard was to give you an idea how small the shifts are.
It seems like there's a bit of a delay.
Yeah.
Yeah. The shifts are about 1/100th of a single pixel on HST, and we need to measure, therefore, to a precision of about 1/1000th of a pixel to see that shift well.
Okay, so now you're using the variation, or you're using the interpixel, your measurement smaller than the size of a pixel on the camera, and getting the positions based on where it is on the pixel. in order to do that accurately, you're saying you've got to be able to do that to within a even smaller degree than the pixel size. Is that right? Am I getting that right?
Yeah. Yes,
Okay.
that's right.
Okay. Well, so who thought this up? Was that you, Adam, or was it Stefano, or did it come to you from a? Oh, I think we lost him again.
Well, so actually this was not invented specifically for this purpose. Adam and I figured out it could be used for this, but originally they developed this technique, the WIFI3 group at STSCI developed this technique to be able to observe very bright stars which had planets. And so they could measure their brightness, even though they were so bright they would completely flood the camera. And also they could see how tiny variations in luminosity.
Sorry, the network seems to have slowed.
When the planet was having a transit. But then Adam thought we could hijack this technique for our purposes, and that's where I also started to help.
Is this something that ground-based instruments can do as well, or is it primarily something well suited for a space telescope?
Well, they could do it, but they couldn't do it with the kind of precision that Hubble has.
Yeah, because that's the one thing Hubble has that most
right.
Most ground-based. Go ahead, Adam.
Right. Hubble already has a factor of 10 better resolution than most ground-based telescopes. So you already start out 10 times better. Then you use this technique to get 10 times better still. If you use the technique from the ground without Hubble's resolution, maybe you could get as good as Hubble's resolution without the technique.
So yeah, we should talk about that a little bit. One of the things that space telescopes, and Hubble in particular, has over ground-based telescopes, because let's face it, Hubble is not the biggest telescope we've ever used to look into space with, but it is got a vantage point that makes it truly unique in the sense that it doesn't have to worry about the atmosphere. The atmosphere smears everything out. I don't care how good your telescope is on the ground, you've still got to look through the atmosphere. And that's why you always see these people building observatories in high mountains, but not just high mountains, high dry mountains, like on Mauna Kea or in the mountains in Chile, because they are very good they have very dry air that is relatively stable. And even with that, though, they still can't get as nice of a resolution as Hubble does, unless they use tricks and techniques like adaptive optics and things like that, where they can really do a pretty good job. So Hubble, being almost 25 years old now, is still being discovered, used in truly novel ways. Like with Frontier Fields using galaxy lenses or gravitational lenses to see further away, because the mirror is only as big as it is. It can only see so far back. They use gravity lenses to boost its power. Here's another technique. By averaging, or not averaging, but getting statistically more measurements over time, where they're able to increase a measurement that's really hard to make, like Adam said, 10 times better. Now, why is it so important, guys? And I'll give this to either Stefano or Carol or Adam, whichever one want to answer this, but why is it so important to know these things so precisely? Why can't we just have a rough idea?
Well, Stefano can go ahead.
Okay, go ahead, Stefano.
So the trick is that these stars are special. The Cepheid stars that we're observing are special. They vary periodically, in a very stable way, and their variability is a very good indicator of their luminosity. Now, they're also very bright, which means we can see them in distant galaxies. So basically, these Cepheids can become and are becoming our primary ruler to measure the size of the universe. So basically, if we made an error of, let's say, 5% in the distance to a Cepheid, we make an error of 5% in our ruler, and so we wouldn't know.
But now I should point out that you're talking about something different now. You're not talking about parallax anymore. You're talking about a new way of measuring distance, which is in Cepheid variables. And
well, the thing is that if you only measure Cepheids that are close to us, then you've only calibrated the Cepheids in our region. Then you say, oh, all the other Cepheids are the same. Well, what if they're not?
Right.
You really have to directly measure Cepheids further and further out so you can make sure that we really understand Cepheids as we move out in the universe, and then we can rely on them as a measurement tool.
Okay, so I want to go back. We got to take a quick step back here. We've already talked about Cepheid variables. These are variable stars that get bright and dim again, and bright and dim again, and the period, the length of time it takes them to go from one brightness to another, that is related to how bright that star really is. If you were standing right next to that star, you would know how bright it is intrinsically. Well, we can get that by watching how it gets bright and dim again. That's called its intrinsic brightness. Once you know something's intrinsic brightness, you know how bright something is if you're right next to it, and then you see it far away. It's a simple well, not simple, but it's a calculation you can do to figure out how far away it is. If you have a candle right next to you, right next to your eyeball, it's a certain brightness. You know how its distance is 0. You move that candle 100 feet away, it's going to be dimmer. You measure the difference in brightness, and you can figure out how far away it is. But you got to know to begin with how bright it really is if it's right next to you, and that's what they're talking about with these Cepheid variables. Is its period of brightness is related to its luminosity, and by doing the parallax measurement on close stars, you get a better idea of that variability, right, Carol?
Yeah, intrinsic brightness. So that now we've measured, you know, it's not a 60.5 watt, you know, light bulb, it's a 60 watt light bulb, if you will. I mean, it's reducing that error, but it's also using the fact that it's a direct geometric measurement, because this thing of things moving around, I go back to your diagram, it's really angles that we're measuring, and we're using the geometry of the situation, and that movement is a measurement of an angle. As we see our target object moving back and forth relative to the very distant things. So it's really geometry.
I've got an animation here that I want to share that might help with visualizing what we're talking about. So let me put this up here real quick. And there we go. So as everything's moving around, we're seeing that these stars are moving compared to what's behind it, or what's behind it compared to that star that we're focusing on.
So yes, you're seeing the orbit of the Earth going around.
These little TV screens come up and show you how we measure the stars as they move back and forth.
So that's what you're actually measuring, that shift there, the back and forth motion.
And the further away, the smaller the motion, and if you're limited by your technology, then you can only measure them so far out, and now they've improved the technique so that they can measure it 10 times further away.
And now we're limited not just by the technique, but also by the Earth's orbit. If we were trying to make these from Mars, we could do an even further job, right?
Well, maybe end of life we'll put it out by Jupiter, and we'll have
or even Jupiter,
we have to wait a long time for
that's right.
Jupiter. Yeah.
It's a lot longer than 6 months before you have to take the measurement. That's for sure.
So this just going back to this this new measurement with Hubble. Is this a new technique that you've developed specifically because you've got this instrument in orbit, and it's an old space telescope now, and you've just basically applied it in a new direction and discovered new things with it by applying this brand new method? Is this a new method, or is this a known astronomical method with telescopes?
Well, I would answer it this way: it was a method that was developed for Hubble to allow it to observe very bright objects without saturating, like exoplanet transits.
Okay.
And we had repurposed it for measuring tiny angles.
So could this be used for like the James Webb Space Telescope? Is this like something that could be used on the next generation of telescopes to make them incredibly powerful? Because we're going to see observations like we've never seen before with the JWST. So could this be used to complement those observations by advanced telescopes to help us see even further, to actually gauge high precision distance measurement of the universe?
Stefano, would you like to answer?
Yes, well, it can be used by other telescopes. What you need is something that's really, really stable, like HST is, and GWST hopefully will be as well. And then you can use the same method. The details are going to be different because the images are taken in a bit of a different way for web, but the basic technique is going to be the same, can be used just as well. And then maybe we can go to fainter objects. One of the problems we have is these stars that we're using have to be really bright because we're moving the telescope fast, and so if they're not bright enough, you don't get enough photons, enough light in each piece. But with Webb, you can apply the same technique to fainter objects, and maybe even with better precision.
Okay. Now, I don't want to rain on anybody's parade, but I just pulled up a paper from 1995 that quotes data taken on a photographic plate by Christian and Racine at the Canada-France-Hawaii telescope, and they used star trails to measure the relative motion of stars and objects, more similar to the planet application that they were talking about was originally created for HST. So it has been used in ground-based on data that I took.
Oh. So you did intend to rain on parades.
You were the pioneer.
No.
We knew it.
Very nice.
That's why you were chiming in.
On the web. Serendipitously. It's embarrassing. Sorry. But
okay, we only have Adam for about another 5 minutes, and we got to go. But I want to get to one of the questions. One of them, this is from Tomas Nocetti, who is asking, what were the first things measured with this new technique and why? How about you? Why don't you take that, Adam, and then you, because you got to go soon.
Okay. Can you hear me okay?
Yep, I can hear you. Go. Did you go? Oh, okay. Stefano, how about you?
Well, for us, in terms of this new technique with Hubble, the first objects have in fact been these Cepheid variables. They're so important to us because they're basically going to be our ruler for the size of the universe. But in terms of using just the trigonometric parallax method, that's been used for over 150 years, and to find the distance of all nearby stars, because it was the first way by which we could tell how far any star at all was. So it goes back to about 1860. That's when it was first used. But this new incarnation that with HST, with Hubble, it has been used so far only for Cepheids.
Okay, and again, it's like you're doing two things at once here. You're kind of confirming what we know about Cepheid variables and their brightness, the luminosity and periodicity relation, as well as getting more accurate actual geometric measurements of these things. So it's kind of two things at once. Hugo Berman is going, so it's still a parallax method, just more precise. And yes, the answer
is correct.
That's right. That's what it is. Okay, and one more question from Hans Milling, and then Adam, I understand you've got to go. So what is the precision of these measurements? I guess they are more precise on closer objects than the old method, but at the limit, 10,000 light. But at the limit of 10,000 light years away, or in this case, I think you're saying at 7,500 light years. How precise are they? So at the limit, how confident are you?
So we're still working on tiny details because this is very
right. So we think at that distance, at the distance of about 7,500 light years, that we can measure distances that are good to about 5% precision. So 5% uncertainty.
Okay. So there you go. So that's pretty good. And before we couldn't even get out that far. So this is quite an improvement on using this, and it opens up presumably a whole bunch more targets that were previously unavailable by this method.
That's right.
That's going to increase our knowledge of Cepheid variables. I wish I had time, Adam. I want to talk about Type 1a supernovae, because that's where you made your mark, and so I guess I'll have to wait until another time. Will you come back? Will you do another one with me?
I will come back with a better connection.
Very good.
Thank you. Thank you. I understand you've got to go. Next time I want to talk to you about Type 1a supernovae, the expansion of the universe, and the accelerating expansion rate. I want to get all of that because I just love talking to you about those things. So thank you, Adam, for showing up, and I understand you've got to go. So again, thank you so much.
Bye, Adam.
Okay, so Scott, did you see any other any other questions? I've only been looking at the Q&A app.
Okay, so I'm looking through because a lot of the comments were first done on the announcement, so I'm having to go through the Hubble page,
Okay.
and also a little bit on YouTube, which is more on I love that Dave English, even though it was being a little bit of a cynical comment here, says didn't cavemen know about sine, cosine, and tangent? Which,
Yeah.
not really. That was developed more with
later.
with the India and the Arabic world. But it's amazing being able to use this very simple mathematics to be able to measure our stellar neighborhood. And now that we're able to go out further, we're able to use these newer methods, these standard candles, compare them to what we already know to get more accurate measurements of our close neighborhood, so we can more accurately know things more further out that we can't directly detect with parallax. But now that we have a more precise way of knowing what's close to us, we can use that as a more precise tool. So, and it's, again, something that was discovered in the last millennia as far as sine, cosine, tangent, being able to use trigonometry in this
I don't
way.
think cavemen knew about that stuff.
Cavemen didn't know about it, but
I don't know what that's
Might have
supposed
done.
to do.
I think it was more of a cynical comment. But
Well,
there's a really good book about that. It's called The House of Wisdom, and how the Eastern world did discover these things, and now we're still using this very old mathematics to discover our stellar neighborhood.
Well, geometry works.
if I can add a comment,
Go ahead.
Yes, kids, pay attention in mathematics.
Yes.
if I can
That's
add a
useful.
comment, actually the Greek astronomers tried to measure the movement of the stars, and because they couldn't see it, they knew they were far away. They just didn't know how far, because when you can't measure something, you can't. So they knew they were much further than the moon, which they could see the shift on the moon due to the Earth's size, but they could not see the shifts in the stars, and so they knew they were much further away. So yeah, the method is old, but it's only become very applicable in the last 150 years.
In addition to that, I mean, like when using these, high precision measurements with Hubble, is there any warping due to, space-time warping due to gravitational fields around heavy objects? I mean, is that a factor you need to work in, or are the distances just too small to really make that a significant problem? Because I know with frontier fields, Hubble's being used to, analyze these lensing effects by the gravitational field of massive galaxies and clusters. Does that affect parallax measurements when you're looking over these longer scales with Hubble?
That's a good point.
Is that a question to me?
Anybody, yeah.
It is, in principle, yeah, you could see the motion of objects, or the apparent motion of objects, because light is going past a massive object. I mean, that's how, for example, general relativity was verified by looking at the motion, at how stars got displaced during a solar eclipse in the early 1900s. And you could design an observation to see this tiny shift due, for example, to Jupiter, and that would be an interesting test and measurement to make. As far as the parallax is concerned, unless you're really, really, really unlucky and you just have a Jupiter go in front of a star you're measuring the parallax of, then no, the motion due to the Sun or Jupiter or any other solar system body is not really large enough to make a difference.
Okay.
But in principle, you have to worry about it. You just have to be very lucky or very unlucky, depending on how you look at it.
So the precision of this new technique then isn't really affected by something like that, those shifts due to planetary-sized bodies then?
No, basically, if you take Jupiter, if you get within 20 or 30 radii of Jupiter, then you can see the deflection due to Jupiter fairly clearly. But it's that level. Mm-hmm. That's less than the size of the Sun, basically. Well, actually, it's just about the size of the Sun. Okay. If you were more than a degree from Jupiter, you can't see it.
Well, that brings to my mind something that I had heard. There's also an astronomer at the Institute, Kailash Sahu, who has discovered a way, or at least he's developed a way to use microlensing to find stellar-sized black holes, and that's these sort of lensing events where stars or some object will move in front, or it will the black hole would move in front of a star or something in the background and cause a small microlensing event, and that little flash is one thing they can use to find things that maybe they wouldn't ordinarily be able to see. But that's not what we're talking about here. But it brought that to my mind: microlensing and gravity moving in front of or gravitational object moving in front of others. That's something that we also need to have a hangout on at some point, because that's another thing that I find pretty interesting.
Yeah, I agree.
Yeah, we're still taking data for that. So there's another year to go. I'm a member of that project.
Oh, are you? Oh,
yes,
well,
yes,
great.
fingers and many toes.
Oh, I thought he almost had the data for it, though. I thought.
Two out of 3 years. We're taking the 30-year worth of data.
Oh, okay. Now, well, okay, great. So I want to ask you a quick question then. How are you doing that? Are you looking at large areas of the sky?
Okay,
are you just putting together mosaics? What are you doing? To
we're
find these
looking
events?
at an area around the galactic bulge where there are hundreds of thousands of stars within a single field. And
Okay.
so, because these microlensing events are rare, so you need to look at many stars before you're lucky enough to see one.
That's right.
And so we are looking at this region near the galactic bulge, which has about 300,000 stars per field. So imagine just one camera shot, 300,000 stars. And then the chances are that one out of about 1 million will have a microlensing event. So by taking many observations, we probably should be able to see about maybe 10, 30, 50. We don't know exactly.
Okay. Well, good. I'm glad I brought that up then, because look for me to invite you. So in about a year, you expect to have something to talk about.
Yes.
Oh, good. All right.
I wanted to go back to the distance thing.
Yeah. Sorry.
I just wanted to mention that the reason that we like to take the direct measurement is because it's geometric, and we can measure directly the distance between the observer here on Earth and that object. But then we need to go further out in the universe. And the reason that you want to push the direct measurement out is because then the Cepheids will overlap with other known objects, and then you can bootstrap your way out. If you know how bright the Cepheids are and they're near something else that you know pretty well but not perfectly, then you can move out with more confidence when you build your distance scale. So that's the reason for worrying about trying to push the direct measurement further out.
Yeah, that's an important point. I don't think we stressed that enough in the beginning, is that, parallax is been one of the most reliable ways of knowing how far things are, and so to get this as accurate as we can is just too bad. You can't
Everything else relies on how well that particular how the nearby stuff is measured. The more precisely we measure the nearby stuff, the better our whole ladder is all the way out.
So that reminds me of a question, Stefano. What about proper motions of stars within our galaxy? Does this help us get a handle on that too? Like, you're looking at where a star is at one point, let's say, I don't know, 2014. We go back in 20 or whatever it is, another years later, and look at it again. Can we get some idea of how it's moving in the galaxy?
Oh, yes, absolutely. There's one little trick, though, which is that it's really all relative. So we can tell very well how stars are moving with respect to one another. But unless we have something that's really stationary, like the distant galaxy or a quasar or something like that in the field, it's very hard for us to tell an absolute measurement of the motion. And so that's going to be the limitation. With parallaxes, there are some stars in the field that we know the distance to, well enough to actually give us a basis, a starting point. But with probe motion, it's a little harder. But yes, in principle, you can see how stars move with respect to each other very precisely with this method.
That makes sense, because we're also moving in the galaxy, and so you have to disentangle all these motions to find out what the actual motion of the star is. Okay, well, Stefano, I know you've got to go too. We've used up all our time with you as well, so I want to thank you for being with us. Look for another invite with you and Kailash. I want to talk about microlensing and finding stellar-sized black holes.
Okay.
Oh, wait, there's a question?
There's a question on Gaia.
Oh, okay, go ahead.
which I love. I love Gaia anyway. So, how do you compare this method and Hubble's ability to ESA's Gaia mission? So, with Gaia going out and essentially making a 3D map of 1 billion stars in our galaxy, how does this help us? Does it have any relation with the Gaia mission at all?
Well, Gaia is going to do a fantastic job of figuring out what the galaxy is like, where everything is in the galaxy, how fast it moves, and so on. For an individual star, like for example for one of our Cepheids, we can do pretty much almost as well as Gaia, or maybe even a little bit better. It depends. Of course, Gaia just was launched in December, so we don't know exactly how well it will do. But if you look at the planned precision, we are going to be very close to its planned precision. And depending on how bright stars are, we can do even better. But Gaia will measure many more stars. So in a sense, they are going to be complementary. We can do better maybe on targeted stars, especially those that are kind of a little bit fainter, because Gaia is a very small telescope, about 1 meter by half a meter. But on the other hand, Gaia will do many more stars. So I would see that as basically reinforcing each other.
Very good. And actually, real quick before you go, Stefano, there's another question here regarding another mission, actually tying in with the big announcement today. So, are we able to measure the distance to exoplanets using the method, using this method via the retasked Kepler mission? Is Kepler with its 2 flywheels now able to precisely that, or is the wobble going to be too great to allow for any precise measurement using parallax?
Kepler was designed to do extremely precise measurements of light, not so precise measurements of position. It uses very big point spread functions, so to speak. So it makes the star images big to measure the light better. So, but we could use HST to measure the distance to the stars for which Kepler has found a planet. Yes.
Okay.
That's definitely something that can be done. I don't think Kepler would be ideal for that purpose, and the fact that it can only point in a limited way now also, of course, makes it much harder. In fact, impossible, as I understand the restrictions on its pointing.
Wow, good question. That was a great question. Yeah. Okay, so
we can reinforce each other as well in that case.
Well, I think that's a big important note to make, is that there are many of these missions out there. We have, we have Hubble, we have Gaia, we have Kepler, we have these amazing space telescopes, and they're not standalone. There are ways that we can collaborate and build better data with these different types of measurements, with the different detectors on there, what their capabilities are, to get a better understanding of our universe by using them together collaboratively.
Yes.
Exactly.
Very good point.
Well, Stefano, again, I want to thank you so much for joining us, and look for more invites. I hope you'll do another one with me when you and Kailash get your data all set and published.
We'll make sure to have a good connection.
Well, your connection was fine. It was Adam's we had a problem with. So, yeah, so you were great. So thank you so much. I appreciate you. Okay.
Bye-bye.
Okay, so I guess before we close, Carol, don't go yet. I want to talk a little bit, since we got a few minutes. I think we've got a few minutes. I want to talk a little bit about Kepler. 180, what was it, 87F or whatever it was?
186.
Yeah,
186. Yeah, sorry, I'm getting ahead of myself, aren't I? Yeah, did you watch that, Carol? Did you see that?
Part of it. I did get called out to another meeting.
Oh, you got to go? Oh, okay.
No, I did during the press briefing. I was asked to go to another meeting. So anyway.
Oh, okay.
Yeah. So it's a multi-planet system, and so they have been able to determine that it's about the right place, and they have made an estimate of its mass. Another thing that it would be nice to know is what its size is, because they were explaining that if you knew the volume, then you can tell what it's made of, whether it's rocky or whatever. But it's a really nice announcement. This is showing, this is showing, number one, which they always said, is if they got to take data longer and longer and longer, they would be able to find smaller and smaller planets, which they have. Mm-hmm. And the ingenuity of using that telescope, even though its reaction wheels aren't working very well. So, my hat is off to them, because they've really persisted, and they are trying to make the best of their situation, and they're doing well and going through their candidate list and trying to verify those planets. So that's very exciting, I think.
Yeah. So let's summarize for those of you who don't know what we're talking about. Scott or Ian, you want to give a brief summary of what the announcement was?
Go for it, Scott.
So, pulling up, there's some beautiful images here. I'm trying to pull up the.
Yeah, it's the images that made this story.
The images are beautiful.
There's a few
Okay,
assumptions made.
while you're pulling them up, I'll just give a brief. So they've discovered an Earth-sized planet. That's really all they know so far, like Carol was saying, around an M-class dwarf star. They're calling it Kepler 186f. It's around the star Kepler 186, which is the system itself. And here's Scott showing a diagram of what the system looks like, a schematic of the size of it. As you can see, it's tiny. Looks like it all can fit in the orbit of Mercury almost. And it's roughly the same size as the Earth, as you can see in the inset there. They don't know if it has an atmosphere. Correct, Ian?
Correct.
I have no idea. I mean, this is the thing.
All they know is the size, right, Carol? I mean, that's, yeah.
They know the size and they know its orbit.
And they know its orbit.
And so its orbital period is 130 days. It gets around 1/3 of the solar radiation from its star because it's an M dwarf. So it's a red dwarf star. So it's not getting as much radiation because it's not outputting as much as our sun is. So that's why, with its orbit being smaller, and it's not receiving as much. We're expecting something that close like Mercury would just to be blasted and bombarded, but since it is a cooler star, we're not having to worry about that. So its heat on the surface is not going to be known until we understand what the atmospheric environment is.
Yeah.
Because that plays into, that's how we have surface temperatures that are stable on our planet, is because of our atmosphere.
Yeah, and I remember David, I think it was David Charbonneau, came to town and did a talk, and he said basically that he would look exclusively, if he could, for exoplanets or life in the universe. He would start by looking with these dwarf-class stars because they are around forever. They last a very long time. I mean, they have very long lifespans, and chances of finding life around them would be much greater around something. And certainly, there's so many of them that the odds are, the statistics alone are enough that make it tantalizing that we're probably going to find something. Sorry, I got distracted by a comment. Be able to find something that more resembles Earth. So, Carol, one thing you said that
if you have a very large, much more massive star than the Sun, that they have two characteristics. They live fast and they die fast. It might not be around long enough to have a planet actually form and have microbial life and things like that.
That's right. The more time
and the larger stars end up varying a lot, and they have star spots and stuff like that, and that means the radiation changes. So that's not so good for trying to have microbial life. So the M stars are some of them have flares, but some of them are nice, small, little, constant stars, and if you have a planet that's close to it and the radiation is right, it would have time to form microbial life and oceans and who knows what.
Yeah. So one thing you said that I want to clarify, though, this discovery was based on data they had taken over the past 4 years, isn't it? They didn't.
Yes.
They didn't. Okay.
No,
No,
my point was that they had argued, even though they were having trouble, that they should be able to keep taking data. It's the 4 years.
Okay.
That in 2 years they can't get the precision for this, and that's why the first discoveries, if people look at the web page or you recall, the initial discoveries were very large planets. So you have a star and a really huge planet, you get the change in brightness. But if you keep staring at some of the other stars, but you need longer and longer periods of time, first of all because you might find different orbits, and also because you need the precision of the brightness to say, oh, was that blip really due to a planet or not? And if it's a big planet, you're more confident, but if it's a little planet like an Earth-sized planet, you need it to go around many, many, many times, and you need to be monitoring that brightness change to a very high precision. So that's why you need a long time scale to keep staring at these objects.
Yeah, and I guess based on the teleconference, they're going to be deciding. It's being reviewed now. This whole solar wind pointing method they've devised to kind of stabilize. They're going to decide if that's what they're going to do or not.
Right.
So Craig Landon leaves the comment real quick. He says, "What can we do to provide Stefano Casertano nicer accommodations in order to ensure that he is willing to return for more hangouts?"
Buy some books.
Well.
Well, I asked him about that. I said, "Where are you, Stefano? Are you in a warehouse?" And
he's in a boxcar traveling the country right now with his MiFi.
This is a great.
Oh, put a blue screen behind him.
Yeah, it turns out he's in temporary accommodations. He's on sababbatical, and that was where those were the office arrangements. We
did a great interview with Leroy Chow, NASA astronaut, and he was talking about space food. And one thing I was very aware of, he was basically inside a cupboard. He had all his clothes up behind him, socks hanging out of the cupboard. It's like, dude, really, you don't have to be in the cupboard for this.
Right.
The glamour of science.
Yeah, the glamour of science. Yeah, when you're on sabbatical, you get what they give you.
So, always make sure there's some books behind you if you're an academic.
Yeah, so maybe we need to hang a picture behind it.
Right. Yeah, exactly. And the remainder of that comment was, or show Dr. Isa our appreciation for persevering through the Hangouts with the network connection. I promise that the next time I have him in a Hangout, I didn't get to control where he joined from, but I think he was on a wireless connection that simply was overloaded at that point. So I want to make sure he gets a better connection next time. Okay, guys. Well, I guess anything else?
I'm going to ask one quick question real here from the Q&A just to go over what, as far as individual stars. That's from Paul Gracie. It says, for measurement of stars outside of our galaxy, can we use the parallax of our transit with the sun along with its path around the Milky Way? So stars that we're able to measure directly like this are within our own galaxy. Because that's how we're able to see these individual stars. The only time we actually get to see any big references to individual stars in other galaxies are when they're supernovae, when you have these big, when they really shine out, and we're able to see these very special moments. So being able to measure long distances like that using geometry would not be able to be used for other galaxies. It's going to be within our close neighborhood of 7,500 light years now.
Well, right, and our orbit, the orbit of the sun around the galaxy is like 250 million years. So
that was the question I was going to ask you.
You can't use the diameter of that orbit, and you can't use an orbit segment because we don't know it that very precisely. So you have to know that baseline very, very precisely for this to work.
Yeah, but that's a good question. Yeah.
So when I live forever, I'll make sure to make these measurements for you guys, and I'll let you know what's going on.
Well, we should just send something and have it sit next to Jupiter, and then we have a bigger baseline.
Yep.
My solution.
Let's just go to the Oort Cloud. Let's just go all out.
We can do that, and that'll take a very long time as well.
Yeah, we'll need a lot of patience for sure. We need a lot of patience. Well, I remember the early days in astronomy, everybody thought it was static. They just did not see that much change in the sky, other than comets appearing or planets orbiting around and doing their retrograde and things like that. It was so static, and now there's a whole field of transient astronomy, looking at things that change on time scales of months, days, and years. That I think
that's not astronomy being run by.
What do you mean by I remember? You're not that old.
I want to marry you, Carol. I'm gonna marry Carol now. So that's.
You read that people thought that. You were not old enough to remember that.
I'm gonna marry Carol. Okay, one more question.
I thought Tony was doing his own research on the luminiferous ether. I think that's how old Tony is.
On ether, yeah. Oh my God.
Oh, geez.
Okay, so real quick from Tomas. Again, one more. Would measurements be necessary? Would it be better would the measurements be better if the Hubble telescope was stationary, not in orbit, or are we in motion with our galaxy regardless, so it wouldn't be still? I think the spirit of the question is, does it matter if Hubble is orbiting the Earth while it makes these measurements?
No, whatever telescope on the ground or in space that you use, it's going to be moving, and that doesn't really affect it because we have stabilization, and we can hold. I mean, if you look at the beautiful pictures that Hubble takes, it's very stable. It can stare at a place in the sky at very high precision, and that's why this works. Is because we know if we trail it, it will be very high precision. So Hubble's okay, being in orbit, it can be stabilized to look at one position, and we take advantage of that 99 and 44/100% of the time, and it's only in these special cases that we actually drift it.
Yeah, so and Hubble uses gyroscopes to point stably, and those were just replaced in the last Hubble repair mission.
Yep.
So
Very stable.
It's basically a brand new telescope after that. So okay, guys, I think we'll stop there. I don't see any other questions. So, yep, thank you, Carol, Ian, and Scott. I want to thank you all very much for helping out today, and hopefully you guys will join me in some more Hangouts in the future.
You bet.
All right.
We'll be back.
Okay. All right, thank you, guys. Well, that's it for this week, or that's it for this Hubble Hangout.
That's a wrap.
Thank you guys for watching, and as always, keep looking up. Roughly light years. I'm having to
150 light year.
About 150.
Right.
Okay.
So with this new technique, we can measure well out to about 10,000 light years.
Oh, okay.
So jump.
Yeah, that's okay. I want to get to that. So let's talk about this. I'm going to pull up this diagram that we have from the press release, and I would like you guys to talk about this a little bit. It says here that generally we're able to see things. Up to now, according to the way things have been done, about 750 light years away. But you guys have found a way to increase that by a factor of 10. What are you guys doing that makes it? I mean, that's quite a big jump. How a factor of 10?
Yeah.
I mean, wow. So what's going on here?
We just try really hard.
it's magical.
That makes most of the difference, it turns out.
Well, I guess
people have
a little bit of space elbow grease and you're good.
No, it's a very clever technique.
Well, let's hear about it. Let's hear about it. So, according to this diagram, now you can see things, or you can measure things reasonably well out to about 7,500 light years using this technique. And these are all, by the way, I should mention, stars. This obviously because of the distances involved. We're talking about things in our galaxy. So we're not talking about other galaxies or things like that. We're looking primarily in our own stellar neighborhood, more or less. So Stefano, what happened? The Hubble Space Telescope is almost 25 years old, and here you guys are figuring out new ways to make it even better. So what's the deal?
Well, what's happened is that we found a method. Adam and collaborators and myself have found a method to actually do 1,000 measurements in one image of the same object. So basically, what happens is instead of taking
nearby objects are called Cepheid variables. They change in a very particular way that we understand, and when we discover them and we measure how bright we see them, and we know how intrinsically bright they are, then we know the distance. And then there are other objects, and one of the most distant objects that we can use are supernova, and that's what Adam and his colleagues have been measuring. But it turns out that going back to the direct method, this parallax method is very powerful because it's a direct geometric measurement, and so there's no modeling or anything like that associated with it, and that's what Adam and his colleagues are going to talk about.
Okay, so so the geometric method you were talking about, that's called parallax, and up to now it's been, I think I read that it's the more reliable way, the most reliable way to measure how far away something is, because it's a direct measurement. We're actually...
Yes, it's a direct measurement, and we're not modeling anything. We're not saying, oh, the star or the galaxy or the cluster should be this bright or this temperature. We don't have to model anything. It's a direct measurement. It's just how we do surveying on the ground.
But it's not accurate, like you said. It's only good for a certain distance away, right? So Adam...
Yeah, and then you can't take images that, I mean, traditionally telescopes couldn't take such precise measurements out to at a certain distance. Then you never see the star. It never changes place. So then you can't measure the distance.
Yeah, the way I always describe it to people is I say, look, you take your finger and you hold it out at arm's length.
Well, yes, and that's parallax because you have.
That's right. That's what I'm saying with the parallax and
observation A, observation B.
Yeah, and you blink one eye and then the other. And you'll see if you look against the background walls, whatever object you're looking up against back there, it will appear. How are you?
I'm good. How are you?
I'm good too. I want to talk about stellar distances, and I wonder if you could give us a background, just a little bit of background on how do we know how far away stuff is out there?
Yeah, exactly. So this will be a really short because there are many methods because astronomers are very clever, and the thing is that we can't go there. So on Earth, of course, we use a tape measure or a ruler, and we also use surveying. So you probably either have used survey tools or you've seen people use surveys like to measure a road, a building, something like that. And the way that works really is that you take a reading from one position and then you move to another position and you use geometry. You know the distance between your two measuring positions, and then you can figure out from geometry how far away something is. And so in astronomy, since the distance are far, we use actually the orbit of the Earth around the Sun. We know how big that distance is, so we take an observation on one side of the Sun, and then 6 months later on the other side. And there's the diagram showing that, and of course we take lots of measurements, not just two, and that gives us the distance to the star. But then we get to distances that are very hard to distinguish when we take the observation, even with Hubble, or traditionally with Hubble, and so the stars are too far away. So then we start using more indirect techniques, and we use things called standard candles, and we also use objects where we can model how bright we think they are, look at them and say, oh, they're a certain brightness, so the distance to them, understanding how light works, is then X or Y. So some of the objects that we're particularly interested in, more.
Hello, everybody, and welcome to our latest Hubble Hangout. My name is Tony Darnell, and I work at the Space Telescope Science Institute. And with me today we're going to have a great conversation about a new technique that involves using the Hubble Space Telescope to measure stellar distances. And with me today is Dr. Carol Christian. She is the Hubble Space Telescope Science Outreach astronomer. Hi, Carol.
There's my little wave.
Yeah, the royal we. Also with me is Scott Lewis, co-hosting. Hi, Scott. And
how's it going, Tony?
Good. And Dr. Ian O'Neill. He's the space editor for Discovery.com or DiscoveryNews.com. Hi, Ian. Thanks for coming.
Hi, Tony. Thanks for having me.
Yeah, thanks for being here. Also, I'm very pleased to have in our Hangouts for the second time now, Dr. Adam Rees. He's an astronomer at the Johns Hopkins University and Space Telescope Science Institute, and a Nobel laureate from 2011. Hi, Adam. Thank you for joining us.
Hey.
And Dr. Stefano.
Good to be here for the second time.
Yeah. You're also is Stefano Casertano also from the Space Telescope Science Institute, an astronomer who has worked with Dr. Rees on this new technique. So let's go ahead and get started. But before we do, I want to mention that you can interact with us in a lot of different ways. You can leave comments and questions on our Q&A app on the Google event page. You can also tweet using the Hubble hashtag or Hubble Hangout hashtag. Whew, a lot of H's.
Oh, that's
Hubble Hangout hashtag. You can also leave comments on the YouTube watch page where this is being broadcast. So we hope you will leave us some comments and questions, and we'll get to them hopefully by the time before we have to close out the Hangout. So, Carol,
yeah.
To shift a little bit based on the distance, because the distance of each vantage point of each eyeball is a little bit different, and so the line of sight is slightly different. And so that's what the effect is we're talking about. And Adam, how good has this been traditionally as a technique for measuring things? Are you there?
Well, it's still pretty hard. Can you hear me?
Yep, I can hear you.
Yeah.
Yep.
Are you hearing me, Tony?
Yep,
okay.
We can hear you.
You know, it's been hard simply because stars are really, really far away. Okay. Stars are just really far away, and so these angles, even when we use as a baseline the whole orbit of the Earth, those angles are incredibly small. Even for the very nearest stars, they're as small as 1 arcsecond, so 1/3600th of a degree.
Yeah. And how far away? When does this generally stop working? How far away are objects generally where you just can't see the shift anymore?
Right. So as technology has improved, we've been able to go further and further out, but that still is only out to a relatively small fraction of the Milky Way galaxy. So the Hipparcos satellite that the European Space Agency used in the 1980s could measure parallax to about 1 milli-arcsecond, which was good enough to get well-measured distances to stars that were, you know, something like under 100 parsecs, maybe 50 parsecs.
Okay, so can you what's that? So 50 parsecs. That's about what in